So we will hear from James Thompson, also from July and Boulder, on photon-mediated interaction for quantum simulation and sensing.
Great. So it's wonderful to be here. I know organizing workshops like this is a lot of work, so thank you very much to the organizers for putting this all together. I'm going to tell you about work we do in my lab at GILA at the University of Colorado. And here's the sort of very, very simple picture of the kinds of experiments we do. Here's the toy model. We get lots of laser-cooled atoms. That's the little balls here. We can control their quantum states. We can make them jump up and down. We can sort of control their internal state. We can rotate it, put it in coherent superpositions. We can do all that good stuff. A lot of people put a lot of effort into figuring out how to do that over the years. Lots of Nobel Prizes were awarded for that. And now we're in the business of asking, how can we not just control single atoms, but how can we create correlations and entanglement? How can we get them to hold hands and do things together? Okay, these links between them. There are many ways to do this. For instance, we heard about ion traps, Rydberg interactions, lots and lots of different ways to do this these days. The way we like to do it is actually to put two very reflecting mirrors on either side of this collection of atoms, let photons bounce back and forth many, many times, about 100,000 times through these atoms. And the atoms can interact with that light and sort of interact. One atom interacts, then another interacts, and that sort of creates these entanglement and correlations. That's a very high-level picture of what we do. Of course, the experiments are more complicated. But the themes are exploring the fundamental science of quantum sensing, metrology, and many-body physics, okay, or the sort of broad themes that we tend to focus on. Great. We are not the only one who put cold atoms between the highly reflecting mirrors here. For instance, Monica and Vladen and Mark and Ben and John and June and Dillman and Jean-Philippe and Andreas Hemmerich, right? So there's a crowd of us doing this kind of thing. We're having a good time doing it. Different groups focus on different sort of areas, but there's intellectual overlap between all of these. In particular, you heard yesterday from Monica, I believe. Unfortunately, I had to miss yesterday. My apologies. Couldn't make it work with my schedule. But in some sense, a lot of what I'm going to talk about today has a lot of overlap with Monica and Vladen and Mark in particular. Okay, great. So we don't just have one of these systems. We actually have 4 different cavity QED systems, this combination of atoms plus highly reflecting mirrors. And so we've got 2 based on strontium atoms that we laser cool and trap. This is a standing wave cavity. We have a ring cavity over here that's actually strontium atoms trapped along this arm of this sort of 3-arm ring cavity over here. We have a rubidium vertically oriented cavity over here. And then finally, I'm not going to talk about it today at all. We have a sort of compact source of non-classical light that we're developing, where we think we can sort of get everything sort of compact down and sort of have a vacuum package, everything that can deliver non-classical light to you with very, very compact. This is in collaboration with John Kitching. He's the expert on this kind of packaging. We're the experts on the QED. Great. So the topics for today, I've got them listed here. I'm going to tell you about cavity QED and cavity-mediated interactions, and then several other topics along here. Along the way, I'm going to do my best. I'm sure I'll be imperfect here to sort of acknowledge the experimentalists who really made the contributions to making this go. These experiments, I'm going to make them sound very trivial. They're very hard. They work very hard. I'm very appreciative of them. In addition, we collaborate quite a bit with theory, incredibly productive and fruitful over here. And in particular, you'll see Anna Maria Ray and her group in this column quite a bit. Okay. So I told you that we create entanglement. And one of the things I'd like to emphasize is that, in fact, these cavity QED systems are quite good for it. Okay. The topic of today's talk is not necessarily quantum sensing, but nevertheless, I think by giving you sort of this introduction to what we're capable of doing, it gives you a sense that these are real systems, okay? So in particular, it turns out I come from a precision measurement background. If we take a collection of N atoms, We actually like to build little meters of the universe, things that measure accelerations or the flow of time or various other things. And at the end, you need to estimate where your meter hand is pointing. There are some fundamental quantum fluctuations that we think of as kind of for spins, the vacuum noise associated with spins here, okay? So when you go to read this out, there's some fluctuations, and the angular resolution in your readout, if the atoms are not entangled with each other, is 1 over root n radians. You can actually introduce entanglement. This is not the only kind of entangled state. We call them spin squeeze states, where you actually squeeze the uncertainty out of the direction you care about it. And I didn't draw it well. There should be more uncertainty in the vertical. So you take the uncertainty out of one direction, put it in the other. There are also things like GHZ states that essentially get the gain, but in a different way. Okay. If you do this, you can build better probes for the universe around us. So here's my attempt to update. I apologize if I've missed your result. Please come tell me. If I've missed something, I'm happy to update this. This is versus time, and this is enhancement beyond the standard quantum limit. This is on a log scale on the vertical. So 1 means you're at the standard quantum limit. It's sort of what you would have with unentangled atoms. And again, this is on a log scale. This is invariance, standard deviation squared. And so early work, beautiful work from Dave Wineland and Didi Liebfried in the NIST ion storage group over here. So you see on here ion traps, cold collisions between atoms, Rydberg-mediated interactions, very recently magnetic dipole-dipole interactions. Squeezed light, here's the best you can do with squeezed light. Let's see, with ions, the best is from Quantinuum at the moment, sitting over here. What else can I point out? Best with cold collisions, Lee Yu's group. For superconducting qubits over here, that's actually sort of this large collaboration over here. The work from my group using sort of what we call quantum non-demolition measurements are these red points over here. And essentially we rapidly figured out, we got our head straight, figured out like how to do this well. Essentially about the most entangled states that anyone knows how to produce are these 2 points up here in Mark Kasovich's group and in our group. Okay, so about 18 to 19 dB beyond the standard quantum limit is about state of the art. Okay, you'll
James, just
yeah.
Kasovich dot. So how is that being? What's that system?
It is the same. Actually, it's funny. His experiment and my experiment look remarkably similar.
Okay.
I take advantage of something called using cycling transitions, and he didn't. And so in some sense, like the details are a little bit different, but in fact, both of these are cavity QED sort of quantum non-demolition measurements. I'll talk about what those are in just a bit. Okay. Let's see. So I will point out that there are some points over here I'll tell you a little bit about today in 2022 having to do with applying this to the first squeeze or entangled matter wave interferometers. And then a recent result, Vladen also had some results, Vuletich here, applying this in the context of optical Las clocks of strontium, trying to apply these squeeze states. Okay, so this is all to say, what's the point? It turns out that these sort of using many atoms and hyphen S cavities, it works pretty well. Okay, so it seems to have legs. Great. I'd like to tell you just a little bit of a story about how you do these quantum non-demolition measurements because it sets the stage for the other kinds of interactions that we can mediate. Here's a prototypical example. This is actually associated with running a Raman matter wave interferometer. Don't worry about the words. There are 2 levels. They're separated by 6.8 gigahertz. I can put atoms in a superposition of these 2 states. There's an optically excited state over here that's 780 nanometers away, okay, as a wavelength. We detune our optical cavity from resonance from this up to E state over here. And that's sort of, here's our cavity. It's a Lorentzian over here. So here's the cavity resonance frequency. Horizontal is frequency. When I put atoms in this state, it actually causes the cavity frequency to shift. And it shifts by an amount that depends on the number of atoms in spin up. And so it shifts by sort of the coupling of the single atom to the cavity divided by this detuning from this excited state. It's just a dispersive shift to the cavity. You can get it from the James Cumming Hamiltonian, okay, in the far detune limit. Great. We can rewrite this shift if you want to write it as a Hamiltonian, as it's, we call it a Q and D Hamiltonian, that somehow the cavity resonance frequency, described by C dagger C here, what sits in front of it, depends on the number of atoms in spin up. Okay, great. The trick here, compared to most measurements of the number of atoms in spin up that you might make in a lab, is that this shift that we measure by sending probe light through the cavity does not reveal which atom is in spin up. And that's the key point. It does not cause single particle collapse. It's a collective measurement of the total spin projection JZ without the universe gaining information about which atom is in spin up. Yes?
Is the G the single atom coupling?
It's a single atom coupling, correct?
Does it change with the number of atoms in the cavity?
No, that is the single atom coupling. And so basically, as you pile more atoms into the cavity, sort of your expectation value of N up would go up, for say after a pi over 2 pulse. Does that make sense? Yeah. Please feel free to ask questions. Okay. So here's an example of quantum non-demolition. The basic idea conceptually, as an experimentalist, is like, I have noise in my lab all the time. I just measure it and I subtract it out. Okay. Why should we treat quantum fluctuations any different? Let's just measure the quantum fluctuations and subtract them out. So here's what it looks like. We essentially replace that sort of N up Hamiltonian. Think of it as effectively we're measuring the spin projection JZ with those cavity frequency shifts. We place atoms in superpositions of spin up and spin down. And then we measure the spin projection JZ via the cavity frequency shift, and we label the measurement outcome JZ sub F for the final measurement of the spin projection. Okay. Now we can prepare two different coherent spin states over here, and you can see that there's a red coherent spin state and a blue coherent spin state. If we prepare this spin state, we measure JZ final here, and we plot it versus the trial number. So these are independent trials. You see the scatter? That's the vertical blue, that's the vertical fuzziness. That's almost pure quantum noise you're seeing. Okay. The technical noise for here is almost 0. Well, 20 dB or more below the projection noise level. Okay. Now, what about this idea of subtracting out quantum noise by just measuring it before sort of applying additional rotation that distinguishes between whether you're in the red or the blue over here? This, for instance, could come from a Ramsey sequence that you can introduce right here in this sequence. You measure the spin projection JZ and you label the measurement outcome JZ sub P for pre-measurement of the spin projection. And now what we do is we look at the differential quantity here. We look at the differential quantity. What you see is we've subtracted out the quantum noise, but nevertheless, we have not collapsed the atoms because you see that angle is still retained. So we have more angular sensitivity. This directly tells you that you're in a squeeze state. We've gone beyond 1/n radians. About the best we can do is about a factor of 60, which in variance, which translates into about the 18 dB number I was talking about. Okay. There are lots of other groups that think about this, and here are some of the references to this kind of work. This was at about 10 dB, and about the best we've done is the 18. So actually, if I use the real data, it would look quieter. Great. We have been applying this. We've taken all the tricks that we've learned and developed over the years into Jun Yi's lab. He has an experiment with strontium. He is geared towards building an optical Las clock. And essentially, you create a spin squeeze clock in this clump of atoms, and a spin squeeze clock in this clump of atoms, and then you make a differential measurement between them to get rid of clock laser phase noise. That's common mode to the two measurements. And so we can actually see that we can prepare these differential squeeze states. You can look up here and using techniques that we sort of first developed in 2016. Why might you do this? For instance, you could use this kind of measurement to enhance measurements of the redshift due to general relativity over millimeter length scales, which actually Jun has already done without entanglement, but we could push those even further if we can start introducing entangled states into the system. Great. So having told you about the Q&D Hamiltonian, we're going to eventually get to cavity-mediated interactions, and here's our first step. This is a technique that when Monica was back in grad school with Vaughn, along with Ian, they developed. And the basic idea is, here's our cavity mode, and we said that the cavity resonance frequency actually depends on the spin projection JZ. So let's just apply a pump. Let's drive the cavity somewhere off resonance from the cavity. And depending on the value of JZ, it might be closer or further from the pump on a given trial, from shot to shot, which will change the amount of light that gets into the cavity, because the cavity mode will be closer or further from resonance with the pump. And so what that means is that the number of photons that circulates inside the cavity somehow depends on the spin projection JZ now. If we go back to our Q&D Hamiltonian, remember we had this C dagger C JZ, but now C dagger C depends on JZ. You put that in adiabatically eliminate cavity mode, magic, you end up with something that looks like JZ squared down here. This is what's called a one-axis twisting Hamiltonian that can drive you into entangled states. Okay, so basic idea is that this one-axis twisting basically says, and we'll come back to this and see this later in the talk, that depending on how far above the equator I am, if I'm above the equator, I tend to precess a little bit faster. If I'm below the equator, I tend to precess a little bit slower. So it takes this quantum sort of like spin vacuum noise and actually shears it, okay? And actually, you end up with a state with reduced uncertainty along one direction. Okay? This idea was actually put forward by Kitagawa Ueda and Dave Wineland, their group, many years ago. Not this part, the idea of one-axis twisting. Okay. There's another way to actually realize this kind of JZ squared Hamiltonian, and it's by actually realizing something called an exchange interaction. And the first time we saw it in our group was in 2018 here. The basic idea is that there's a clock state. This is a very long-lived state. It lives in this optical excited state for longer than I'm going to spend on this slide. It's crazy. This is what you use to build optical clocks. Okay. So imagine you put one atom in this upper state and another atom in the lower state. You can have a process where this atom emits a photon into the cavity, but before that photon has a chance to escape, this atom absorbs it. So if I think of one of those states as spin up, the other as spin down, this is a flip-flop interaction. It's an exchange interaction for the pseudo-spin over here. And so that's what happens. You get this exchange to the cavity. Because it's all-to-all, every atom is talking with every other atom, we can write this in terms of collective raising and lowering operators, which then you can rewrite as approximately J squared minus JZ squared. And see, we've got this one-axis twisting term there again. We predicted that you should be able to see that this sort of leads to this kind of one-axis twisting dynamics, as well as a kind of many-body gap protection that we'll come back to later in the talk when we talk about something called a matter wave interferometer. Yeah, okay, so here's the observation in the context of this clock transition, using that as our pseudo-spin state. We vary the tipping angle of the Bloch vector, and we look at the precession rate as a function of this tipping angle, and sure enough, we see this linear dependence with tipping, with the spin projection JZ. Okay, that's the evidence that we got the one-axis twisting there. You can also see as a function of the detuning of the cavity from resonance with the atomic transition that this actually is an effect that arises when you're off resonance from the cavity, okay? Because you don't want the photon to escape. So you want reabsorption to happen faster than the photon escaping. Okay. So with that introduction to different ways of generating interactions, I'd like to tell you about our implementation of the LMG model. This was talked about by Anna Maria in her talk. And you should think of it as there was this Dickey model that was introduced by Anna Maria. And you say, in the limit that the photons are slave to the atomic coherence and they can be adiabatically eliminated, then you end up with a pure spin model. Okay, you don't have to worry about the photons. You just have interacting spins at that point. And you can predict some phase diagram over here. We'll talk about that in a second. But essentially, this is exploring new phenomena of equilibrium. Many groups are exploring this, going back, really actually starting with Vladen, I would say. Vladen Voltage was probably the first person to see this transition. But essentially, it's an abrupt change in the dynamical behavior as characterized by a time average order parameter. That's going to be our sort of working definition. You can poke at it, like it, don't like it, but that's how we're going to define it. And in fact, there are many experiments that have also been probing this, and our experiments are closer to the experiments of Chris Monroe and Joseph Thiveson in terms of spirit. Over here. Okay, so here's our implementation of the LMG model. We realize this exchange interaction through the cavity. Okay, this is this exchange of photons between a ground and excited state. We can detune some field, some drive we apply to the cavity by some amount delta. And then we have the transverse field described by the Rabi frequency here, omega. This Hamiltonian is written in the rotating frame of the drive that you're applying. Okay. To do this, we're not working on the clock transition, but we work on a narrow transition called the triplet P1 transition as our excited state, and it has a radiative line width of 7.5 kilohertz. Okay. The cavity has a line width of about 140 kilohertz. Okay. We detune the cavity from resonance by about 50 megahertz, and now this sort of puts us in this limit where we can think of it as a pure spin model. It's a very good approximation. So here's a predicted phase diagram. So let's walk through a cut along this line. So if we start down here, here's the Rabi frequency of the transverse drive. We're going to work on resonance with the transition. And the idea is if we do a quench where we start with the atoms and down, and then suddenly we turn on this transverse drive over here, in this limit, the spin exchange interaction is much stronger than the transverse drive. See, it's big and not small. That's how you know, right? So if you do that, then you look at the spin projection JZ, and you see actually it's trapped. It can't get away from the south pole. Okay. Now we can move up this, and we can see that, well, it turns out due to some like imperfections in the experiment over long times, you're creeping towards JZ equals 0, but sort of at early times, you're not quite at JZ equals 0. If we keep going up, eventually you cross through JZ equals 0. We have some inhomogeneity in our Rabi flopping that causes it to damp. And then finally, we go into the limit where the transverse field totally dominates. Basically, this is single particle Rabi flopping at that point. Okay. Great, so what we can do is we can actually plot the expectation value, the average value of JZ. It's actually a small time average around this window out here. And we can plot that for different atom numbers that we use versus the Rabi frequency of the drive that we applied to the cavity for different atom numbers, 935,000, et cetera, et cetera. If we rescale by atom number, you see these fall on top of each other. And the black over here is the theory from Anna Maria's group. Okay. Great. So this is our observation of the LMG model. It is true that in this paper, we predicted that if you could sort of plant yourself somewhere over here, the state would actually evolve into a squeeze state or entangled state as well. But lots of technical stuff has to be improved if we wanted to look for that. Okay. Now, I wanted to emphasize, and this goes back to Anna Maria's talk, that we are in a limit where, in fact, from time to time, a photon leaks out of the cavity. And we don't want that. Okay, and so we're interested in thinking about regimes where we can go beyond sort of this spin-spin interaction. Oh, shoot. Everything I said right now was true, but I forgot to tell you the other parts. Let me just say we could also explore this phase diagram along other cuts where we vary the detuning of the drive. We can look along this cut. We can look along this cut. Everything agrees with what we expected. We also can sort of take advantage of the fact that we don't have to begin and spin down. We can prepare different initial states and look at how that modifies the position of the transition. Don't worry about it. But we have more degrees of freedom and phase control in the system. Okay. Now, let's come back to what I was saying. In the LMG model, what we'd really like to do in order to get to the kinds of systems that Anna Maria was talking about, for instance, this recovery protocol, we can't afford to have those photons leak out of the cavity. So unlike an ion trap where the phonons in some sense never radiate out and hit the wall, they certainly do in our lab, right? The photons radiate out. So we can't have that. So the idea is, can we instead replace effectively in a Dickey model an atomic degree of freedom as an effective boson-like degree of freedom, okay? And so in order to do that, we'd like to explore and understand more rich systems and different types of systems that may provide more capability to do that, okay? And so with that, I'm going to tell you about some work related to what we call matter wave interferometers, but it's really exploring manipulating both momentum and spin of atoms, okay? So in particular, you may have heard about this idea of using synthetic dimensions. So for instance, you could have a lattice in real space, and then you could have, say, different internal states of rubidium, say F equals 1 of rubidium, M equals -1, 0, and +1 over here. You could sort of imagine having sort of different, like, gauge fields. So you could have effective magnetic fields as you sort of go around these loops using, say, Cloquet engineering to drive you around closed loops here. So people are interested in this. I'm going to tell you a little bit about how we can take advantage and coherently control the idea of momentum space. And in principle, you could use and realize momentum space lattices. But first, we have to show that we can sort of control a pair very coherently to a pair of momentum states, okay? And then the second one, which is actually very related intellectually to what Monica probably has told you about, is the idea that you can also use internal states as your degree of freedom, as your synthetic degree of freedom, just like it was done here. In Monica's case, I don't think I do too much abuse to her work by saying that her space is kind of like the different ensembles here. Not exactly a one-to-one mapping, but so there's an intellectual, conceptual link somewhere in there. Okay. The second part I'm going to tell you about is how we actually are trying to take advantage now of internal states using the 10 nuclear ground states of 87 strontium. So in the precision measurement world, the idea of manipulating momentum states as a sort of a synthetic lattice or something like this, actually, the words we use for that are matter wave interferometers, okay? And in particular, the whole idea is that if you have some atoms coming along, you can put atoms in a superposition of absorbing light and not absorbing light. And so they change their momentum state and don't change their momentum state at the same time. They can go into a superposition of the two. Now, at some later time, you can sort of reverse, sort of the part of the amplitude that, recoiled and didn't recoil, and actually get the two trajectories in space to re-overlap and interfere. It turns out you can build exquisite tests of, fundamental physics over here, as well as technologies, like real practical technologies. I was at a conference, I saw Boeing showing an AOSense sensor being six-axis sensor being flown on an airplane. Son of a gun. It seems to work. It's in a box. There are also connections to Einstein's equivalence principle, and actually right here from Stanford, proposals for using these kinds of things for gravitational wave detection. Okay. Great. So what's our matter wave interferometer? We have a vertically oriented cavity, so gravity is down. So we put some atoms inside this cavity. We're going to let them fall along the cavity axis. The atoms would expand radially. To avoid that, we actually put in a repulsive dipole potential. So it's like a donut, and sort of no intensity on axis, but as it moves off axis, it feels a repulsive force, and that guides it as it falls. For the people who care, here are the experimental sort of numbers going, gone. Great. So we need to first show that in this system we can get coherent control of this momentum lattice. Can we sort of manipulate these momentum states? The way we're going to do this is we're going to apply all of our momentum kicks by driving lasers non-resonantly, so we just crank up the power along the cavity axis. Okay, so all the momentum kicks will be along the cavity axis. And here's an example of what you would call a Raman, but you could also think of it as sort of a spin momentum kind of degree of freedom, where we prepare the atoms in some momentum state here. It's along the vertical axis we're talking about for momentum. And then we apply a light pulse, which is a 2-photon absorption that actually flips sort of half the atoms to this momentum state. In fact, it's a pi/2 pulse. And then we apply a pi pulse. And then we can look at the momentum difference over here, and we do a scan, and we see some at 0 h bar k and half at 4 h bar k. Okay. And so by using these kinds of tricks of 2-photon transitions, we can both manipulate spin and momentum in the system. This will be referred to as Raman. This is referred to as Bragg, where you say, I do not want to change my spin state. I just want to change my momentum state. We simply change the detuning between the two laser tones that we apply along the cavity axis. So we can apply a pi/2 pulse. Up, down, there's an intermediate excited state we're going through non-resonantly here. And then we apply a series of pi pulses to get very large momentum separation over here. Okay, so this would be, for instance, preparing yourself at different lattice sites in this momentum lattice. Okay. So it looks like we've got the pieces here for manipulating the atoms in this high finesse cavity. Everything I've shown, like, that's well defined. No one had just done it in a high finesse cavity before. That's the new part. Can you really make it go inside of a high finesse cavity? In order to show coherence, you actually want to build a matter wave interferometer where you do a pi/2 pulse, a pi pulse, and a pi/2 pulse. We envision these states on some block spheres. North pole is 2 h bar k recoiling, and south pole is 0 h bar k. There's some quantum uncertainty between this superposition. We scan the phase of the final pi/2 pulse. We map out fringes. Aha, there's coherence. It's not just blue and red marbles. We're putting things in superpositions. We can actually see that as the atoms fall, the phase of this interference fringe actually shifts as a function of the time between the pulses. So there it is, t. And the phase accrues like t squared. What else accrues like t squared? If I drop a rock, it like accrues like t squared, right? That's freshman physics. That's all this is. You're basically saying that we can sort of, in a way that involves quantum coherence, we can actually keep track of the phase as the atoms fall. That allows you to build an inertial sensor. Great. So now I'm going to skip over, in some sense, the most interesting part, but I gave you a flavor of it before. We actually, because we have both spin momentum degrees of freedom, we can actually measure how many atoms are in spin up versus spin down. That tells us how many atoms are in one momentum state versus the other via cavity frequency shifts here. Okay, so this is a cavity frequency resonance that's measured in homodide, and then we see when we put atoms in it up, it shifts to over here. And if we do that, we can prepare squeezing in this momentum basis that's about 3.4 dB. We can also apply this one-axis twisting method and see about 2.5 dB of squeezing. Now we can take all, I'll just point out that in comparing these two, you can look at this paper, there's a threshold in your quantum efficiency as to whether you should use one or the other, if your goal is just to create, entanglement. Okay, great. So everything I've told you is about actually starting with an unsqueezed state, running a mini matter wave interferometer where we do one of these two operations to create a squeeze state, and then we actually take that squeeze state and we flip it on edge, it accrues some phase inside of our interferometer, and then at the output we sort of apply another rotation that maps the phase that accrued into J and Z and brings the squeezed direction back into our measurement basis, which is JZ. And so we could see that at the output of this interferometer, we were below the SQL, so we inject squeezing on this end, it comes out this end, and that's the first time that had been done. So we think that this is really going to set the stage for using squeeze states in the future. Great. So this is talking about creating entanglement in the context of spin momentum systems. But can we actually go from a spin momentum, degree of freedom, to just momentum? Sure. So let's see. Collect my thoughts here. Imagine that I had two momentum states, P naught plus H bar K and P naught minus H bar K. P naught is the average momentum of say, these atoms as they're falling along the cavity axis over here. Let's ignore that they're accelerating. We have to do all this in a chirped rotating frame. We just do all of it, okay? We basically keep track of the rotating frame in all of our electronics. Okay, so I apply a pump along the cavity. It's off resonance from some excited state that's not shown here. You can have a process where the blue atom absorbs a pump photon and emits one into the cavity. So this blue atom emits a photon, and then it comes over here, and that red atom can actually absorb it and stimulate to the other state. And in that process of emitting and absorbing, you get momentum kicks. And so they've exchanged their momentum states. So if I think of this as spin up and that as spin down, I can write this in terms of Pauli matrices over here for atom I and atom J inside of our system. But it's all to all, so I need to sum over all I and J, I not equal to J over here. And then I can rewrite this in terms of collective raising and lowering operators, J plus J minus. So we got the spin exchange interaction again, but it's in a pure momentum basis. Okay. This was not obvious to me that this would work. Murray Holland took some of the work that we did in the context of squeezing of the exchange interaction in the strontium system and actually predicted that it should work in this momentum basis. So he deserves credit for that. And Ethreya Shankar, actually.
Is there like a application, like something you'd want to sense with that state?
Yeah, definitely. So in fact, what you'd prefer to do is run your matter wave interferometers, if you could, in a Bragg configuration. So I'm gonna put on my precision measurement hat. You would like to run a Bragg because that way they have the same internal state, and how they couple to the universe is common mode. And so so in fact, you'd really love to do these things in a Bragg configuration. Okay. Mm-hmm. Okay, so can we see this one-axis twisting? We said we should have a total J squared and a JZ squared term here. Can we see this term? Well, remember, we can just vary the tipping angle, sort of what fraction of the atoms went from one momentum state to the other, right? And we look at sort of the precession or the phase shift inside of our interferometer. In fact, we see this sort of JZ. We can flip the sign of chi and see the opposite over here. Great. So that term appears to be there. In order to get to squeezing, we need to improve some laser phase noise at 500 kilohertz offset from the carrier of the laser. It's actually a challenging problem, but we'll get there. The total J squared, this is a funny one. If you think about a matter wave interferometer, if I put an atom in a superposition of two momentum states, it means that the wave packets will separate as a function of time and no longer overlap with each other. This is along the cavity axis in a co-falling frame. So if I hit the system with a pi over 2 pulse, I wait some amount of time t, and then I hit it with another pi over 2 pulse, scan the phase of the final pi over 2 pulse, you will see an interferometer fringe. At early times, let me go back, they're overlapped, and I will have high contrast. But as they move apart from each other, I will lose my contrast on the interferometer fringe. It will go down. So we can actually look at that contrast, that's the black points as a function of time. The delay time over here, that's the wave packet separation that causes this contrast to go away. You lose your signal. This is why interferometers have to put a pi pulse inside of them, typically. Now we turn on our dressing laser to create these exchange interactions, and we actually see the red points. We see coherence lasting much longer than it oughta, okay? So what's up with that? Well, in this picture, it's very clear that the reason you lose your coherence is because the wave packets no longer overlap with each other. So if we see coherence at these times, it means that somehow the interactions have stopped the wave packets from separating from each other. Okay. A similar effect was seen, we saw spectroscopic signals of it in the strontium system, but Monica actually saw it in a spin system, a very similar effect in her experiments. However, this is associated with motional degrees of freedom. So what in my world, we call Doppler broadening, okay? In other words, you might call it like, I don't know, like spin orbit or something. Okay. Great. So in fact, we can do, well, Anna Maria's group can do numerical simulations of when you have the interactions on, what the wave packets do over here. And in fact, they become bound to each other. In fact, they're bound to each other like a spring that has a resonance frequency chi-n over here. And so if we actually pluck the spring by allowing the wave packets to begin to separate, and then we turn on the interactions, that's like pulling the spring apart and then letting it go, they ring. And that's exactly the ringing that you see in these curves over here. Okay. At a very high level, I'd like to tell you what I've just told you. Most of my time, good, I can tell you this story. Imagine I had a single photon source, and I had a chunk of atoms over here, laser-cooled atoms, and I don't have any interactions on. Well, I shoot that single photon into this cloud, one of the atoms absorbs it. If I wait long enough, a single atom will come out. It'll come out at a velocity, which is just h bar k over m, where h bar k is momentum carried by that single photon. Conservation of momentum. Okay. Now let's imagine I turn on these momentum exchange interactions. What would be different in this system? I would shoot that single photon in, and the whole cloud would recoil. Okay. And it would recoil at a velocity that's divided by n over here. So this is like a new collective recoil mechanism. Okay. So if you are in atomic physics, you'll realize how important these concepts are. Mossbauer spectroscopy, which allowed Pound and Repka to see the GR shift for the first time, relies on this kind of collective recoil mechanism. Lambdicki spectroscopy, that's the heart of all of our precision measurements and getting rid of Doppler broadening, relies on this kind of collective recoil of the apparatus, okay, when you tightly bind the atom to it. This is just a new, different object that seems to do something very similar. Okay, but it's involving interactions and superpositions in the system. We also have in mind that in the future, we should be able to combine this to actually realize solitons in our system. But that's a proposal, haven't done any experiment yet. Okay. Solitons meaning that the two wave packets don't separate, but nevertheless, the wave packets continue to spread in space. We could engineer a system where the wave packets don't separate and the wave packets stay localized in space, they don't spread. Like the width doesn't get bigger. Are there any clock people in this room? No, I'm going to tell you this anyways. I've told you a story about matter wave interferometers, and you go, blah, 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 matter wave interferometers. Sometimes I go to crowds, in particular in the whole Boulder area, and there are people who like to build atomic clocks. And they go, yes, that's a nice interferometer story, but we're clock people and we worry about clock things. So we asked, could we actually do this on a clock transition? This is not quite a clock transition, but it is a narrow alignment transition, 7.5 kilohertz. We have a ring cavity. We can put our atoms in this arm. We can send light into the cavity to put these atoms in a superposition of the ground state and the excited state. But they're not trapped, so they're free to move along the cavity axis. And so you get Doppler decay. You lose your coherence between the ground and excited state. Here's sort of coherence squared versus delay time. Given the temperature of the atoms along this direction, here's how quickly you lose coherence between this state and this state. If you turn the interactions on, that's actually data over here. This is what the interaction's on, and we see that we're preserving it. So this also works in the context of preserving coherence on optical transitions, and you can read about that here. I think it's fun. This is not my work. This is actually my super duper grad student who has now moved on to Caltech. Went there, and they have a dense system of ytterbium ions over here, and it interacts with the microwave cavity. And in that system, they can actually see very similar physics. So actually, these concepts are actually now going into the solid state. So it's really fun to see in that system. They see about a factor of 60 improvement in the Ramsey coherence time. Using these cavity-mediated interactions. Okay, so I've told you about this momentum exchange process. I haven't told you how we did it. The cavity is actually, here's versus frequency. The cavity is the Lorentzian here. It's sitting here. We apply a pump that's far from resonance. And there's a kinetic energy difference between the two momentum states, which we'll call omega z. And now the idea is that when I absorb and emit a photon to conserve energy, the frequency of that photon must be shifted by omega z. Okay. And so the process is I emit that intermediate photon. Sometimes people call it virtual. I want to call it intermediate. In my world, it's really there. It's there for a brief amount of time, and then essentially this red atom can absorb it, and that's how we got our exchange interaction in the system. But we can engineer another one if we actually just apply a second pump, and we put it 2 kinetic energies worth away from the first pump. In this process, if 2 atoms start in the same state, we can have the blue one absorbs and emits, and then the red one can absorb that photon and stimulate into the other pump, and we conserve energy by exchanging energy between the 2 pumps. When we do this, now we get pair raising and lowering terms that are all to all and look like J plus squared plus J minus squared. If you want to think about a bosonic degree of freedom, this would look like something like A dagger squared plus A squared in some Holstein-Primakov limit over here. Great. We have independent control of these 2 degrees of freedom because this involves interacting twice with each pump, whereas this involves interaction once with each pump over here. So by actually changing the relative amplitude of those 2 pumps, we can actually change how much of this versus that we have. If you allow yourself to stay in the collective manifold, then it's a very good approximation. This gives you the ability to realize arbitrary XYZ all-to-all Hamiltonians that you can engineer. In particular, there's something called 2-axis counter-twisting. We've heard about 1-axis twisting. This was proposed by Kitagawa and Ueda like 30 years ago. It's kind of been sort of this magical unicorn. It sounds wonderful, but don't know how to do it. This gives us the ability to do it. Actually, there's a related proposal from Monica maybe like 4 or 5 years ago that actually also had a way to do this. It's a slightly different way of doing it, but it's very related. So you basically take these 2 terms. If you actually balance, set the ratio of these 2 together, you get jx squared minus jz squared. And actually, that turns out to be 2-axis counter-twisting. So we can actually look at, there it is. Good, I put it there. Okay. We can actually, this is actually data where we reconstruct flow lines on the Bloch sphere to see whether or not we see the dynamics that we expect from a 2-axis counter-twisting Hamiltonian. So everything I've shown you so far are 2-body interactions. They're all-to-all, but it's pairwise, because if I unpack these terms, you'll see it's sigma I, sigma j, like a pair of operators. So a question we had is, could we go beyond that? So for instance, could we have 3-body interactions or even 4-body interactions? And at first, when you think about it, you go, this is going to be really hard. Why? Because as you go to higher order in the interaction, it means you've got to exchange more photons. And so chi3 is much less than chi2. And chi4 will be even smaller than chi3. You're going to higher and higher order in perturbation theory for these processes. However, my student pointed out, Qingyi, pointed out that, well, the characteristic energy scale that's relevant for dynamics in our system is n times chi2. But if you go to 3-body, it's actually n squared times chi3, and n is a big number. Okay, it's 1,000. And if you go to chi4, it's n cubed times chi4. So in fact, you might imagine that you'll never see these effects, but in fact, we think they should be observable. So we set out to do it. In fact, this was a fun experiment because it worked so fast. It was a lot of fun to do. So for instance, here's a 3-body. How do we do it? We actually just set the frequency difference between the 2 tones to be equal to 3 times the kinetic energy. That allows us to conserve energy in a multi-photon process. It's a 6-photon process. Over here, you can just follow the stepwise, emit, absorb, emit, and close the loop over here. Okay. We can also look at dynamics on the Bloch sphere. Maybe I'll skip over this for the sake of time and just say that we also can see it's a resonant process. So this is the sign that we're seeing 3-body. We think that this can be applied to metrology. It may have some advantages in terms of speed, at least in some limits, but this is a very hard problem to calculate. It certainly creates non-Gaussian states in the system. We could also do this for 4-body, where we separate the 2 tones by 4 times the kinetic energy difference. You walk through the steps of absorb, emit, absorb, emit, absorb, emit, blah, blah, blah. You can conserve energy again, and we can see the consequences. Okay, with the brief amount of time left, I'm going to do this anyways. I'm going to tell you about nuclear spin states, how we're getting control of nuclear spin states. So imagine I had a 1D optical lattice over here, and I was thinking about a process where I start with atoms on either end of the lattice. And I had a process where an atom can only tunnel to the right if an atom on this end tunneled to the left. Okay. And then you can imagine that could continue, that I can only continue to go this way if another atom continues this way. So we can actually think of this 10-site lattice as, say, at least at first approximation, the 10 nuclear ground states of 87 strontium over here. And so we can have a process where an atom moves to this nuclear spin state if and only if an atom moves to here. And then this can continue on down the ladder. This is very related. It's similar. It has distinctions, but it's very related to the spin 1 work in Monica's group that you may have heard about yesterday. Okay. How do we do this? Well, what we do is we apply dressing lasers into the cavity. They're detuned from this triplet P1 state sitting up here. And then we get a virtual process where I emit a photon. That photon gets absorbed, and I come over here. And the only way to conserve energy is going to be if both atoms hop at the same time. Cool. In order to do this, we'd like to be able to read out the state of every one of these nuclear ground states. So imagine I want to measure the populations in each of these states at the end. We had to develop that technology. The way we do that is applying a magnetic field, and we actually split those excited states by 10 megahertz. The beauty here is this is a 7.5 kilohertz line width with about a Bohr magneton available to give you a Zeeman splitting. Compared to, say, in rubidium, where the line width is 6 megahertz, we have 1,000 times more resolution because of the narrow line width. That allows us to work. So by doing that, we can actually tune this cavity by shifting a voltage on a piezo to change its length. We can actually set the cavity to resonance with this transition to this transition. And then we can actually apply probe light and sweep the frequency of the probe light and measure the transmitted power. It's a little more complicated, but we can see that we get 2 mode resonances, which is called the vacuum-Rabi splitting. From that, we can infer the number of atoms that were in this M level. But we wanted sort of full readout on a single shot. So what we do is we actually just tune the cavity to this transition, and we do another sweep. In fact, we just keep doing it. So in a single shot, we just scan the cavity to all 10 transitions and do our readout over here. How well does it work? Well, here's a characterization of measuring a single shot every spin state where we're actually just applying an RF coupling to drive Rabi flopping, single particle Rabi flopping. And this is what you expect in theory. These little knobs over here, this is actually the counter-rotating term that we normally ignore, but it's an RF signal, so the counter-rotating term is not that far off resonance. But here's the data, and so you see that actually, here you start in -9 halves, here's where you hit +9 halves, and then you come back to -9 halves. So that's a 2 pi pulse over here. And you can see you occupy all those levels in between. And remember, that's the quantum fuzziness, right, of a single atom in this, spin 9 halves, right? That you have a spread in M levels when you're at the equator. Okay. So that seems to work. We have the readout capability. How well does it work? Well, we can actually apply light shifts that actually shift these levels, but leave these 2 levels alone to create a pseudo spin half. We can hit the system with a pi/2 pulse to create a superposition of that pseudo spin half. And then we can make 2 measurements of the number of atoms in 9 halves. And we see that the difference of those 2 measurements is 5 dB below the quantum projection noise level. So it says we're starting to have measurement resolution to resolve quantum physics in the system as well. We can also, for the heck of it, measure how much the measurements shorten the length of the block vector. And this says we're probably at about 1.5 dB of Q and D squeezing these ground states. In principle, you can map to the clock state for optical clocks. We think we can make that number better. It's a question of how hard do we want to work on it. But we think there's a way to make that number bigger. Okay. How do we tune the correlated hopping to resonance? It's important that we conserve energy. So we apply, here's frequency, we apply a dressing laser close to the atomic transition. The cavity's far away. This is a weird system compared to what cavity QED folks are used to. The cavity is going to be far away, and we're going to apply all of our dressing lasers close to the atomic transition frequency. So we're going to be close here at some detuning delta R for the red detune pump. The issue is that when you do that, you get a tensor shift on those ground states that shift these energy levels over here. So if I draw my 4-photon process, it turns out I won't conserve energy due to these frequency shifts, due to the tensor shift. So what we do is we apply another dressing laser on the opposite side of the atomic transition up here, and basically we balance it so we create opposite tensor shifts and they cancel. And now that brings us into resonance. If we do sort of a Holstein-Primakov approximation, just sort of generating excitations here and here, this looks like A dagger, B dagger plus AB over here. It turns out that there are other processes as we tune our system around where we can actually get pair production on one end of the ladder and pair production on the other end of the ladder. In fact, this was predicted in theory as you change the relative detuning of these two pumps, the red and blue pumps, dressing lasers over here. So we can go and look for those. If we optically pump all the atoms at t equals 0 to -9 halves, and we scan the detuning of the blue pump, we see that there's a resonance in atoms appearing at -7 halves. We do the same thing, we optically pump to the other end, we see a resonance. This is the other pair production. And if we optically pump into both, then actually we see a new resonance right in the middle, and that's the pair production. Sorry, the correlated hopping, right? Which looks like A dagger, B dagger plus AB in sort of a Holstein-Primakov limit. Okay, so we can actually look at time dynamics. Maybe just for the sake of time, I'll just say that we can sort of map out sort of how all these populations are changing. We can look at sort of steps beyond just the first step. We can start to see population moving inwards in the ladder. Maybe the last thing I'll say is we can go back to isolating this two-level system. We write operators here in the pseudo-spin basis of just this two-level system. This gives us the pair production Hamiltonian. And we can actually measure dynamics equivalent to what we did previously for characterizing the pair production. But we can also see that if we're near the South Pole, that this sort of gives you the dynamics of squeezing at the mean field level. So we really need to be able to push this beyond mean field in the future and start to see that we're creating entangled states. Okay, with that, lots of other fun stories over coffee if you're interested, including emulations of dynamical phases of BCS superconductors. But thank you to the team as well as the funding for making this work. It really takes a lot of people working very hard to make this go, including all of our theory collaborators over here. We're very grateful for. With that, I'll stop.
Questions?
Yeah, I have a question about the sort of momentum space lattice story.
Sure.
So as you said, I mean, that has been explored also without a cavity.
Correct.
And I always sort of thought of it as an interesting analogy to a system we have in our lab where,
Yep.
as you kind of showed, we sort of use frequency space to have some flexible control of couplings.
Yeah.
Bryce Gadway has done this in momentum space with these momentum space lattices. Can you, I didn't fully understand sort of what the goal is with bringing the cavity, and aside from obviously atom interferometry, but more in a simulation context.
Yeah, from a simulation
the
context.
cavity and that together.
Perfect. So you could imagine we have mixed motives on this. Let me start with the story for here. You could imagine that you could have spectroscopically resolved Bragg couplings between different momentum states. So you could think of those as I could just sort of do rotations, independent rotations. And then applying appropriate dressing lasers, you might have processes to allow photon exchange between those spin half in momentum state. Have we demonstrated that? No. But the fact that we can sort of do all this manipulation says that, yes, like all the tools, in principle, it ought to work. You can prepare a spin. Here's my parabola of energy versus momentum. Momentum conservation says we can only use states that are separated by 2 h bar k. So we have some points here and we have some points here. They're omega z's, their transition frequencies are different, so we can spectroscopically resolve them. We can do whatever rotations we want. Now by applying appropriate dressing lasers, we think it may be possible to have photons emitted where you actually get exchange of photons between them, and that would be like between your sub-ensembles. So I think that's the connection to be done. Have we done that? No. We are interested, I'll tell you, so now I'll put on my other hat. We're actually very interested in this in part because we see that there's, as always happens in these kind of entangled systems with large atom number, it's not clear to most listeners that actually you need enormous fidelity in all of your rotations in order to actually see the entanglement. And so by doing this kind of, imagine just starting with 2 different pairs of momentum states, we might be able to drive sort of matter wave interferometers where we get differential cancellation of noise associated with our rotations. And so that would be a first stepping stone. So it has both from the context of creating interactions that are relevant to sort of these emulations and Dickey models, also for differential sensing and showing that you can actually drive into an entangled state in a Bragg matter wave interferometer. If I go to a point where actually the 2 ensembles are also spatially separated, then you can imagine in that case, that you're running a gravity gradiometer. So there's also like, it's not just getting rid of it. You could imagine you use this in the context of a gravity gradiometer. I maybe told you lots of stuff you didn't want to hear, but like that's what we're thinking.
On the theory part, one big advantage of the system is that it goes completely uniform. So the couplings, we don't like homogeneous couplings on the theory. We want perfect systems.
So along that lines, this is the moment where I get to pat myself on the back. Sometimes you do something that you think is clever in the lab. Essentially, we built a ring cavity without having to build a ring cavity. By allowing the atoms to fall along the cavity axis, we get a separation of timescales such that we essentially can treat the system like a ring cavity. And that's very pleasant. It opens up lots of things that you can do. You basically move from thinking about clockwise versus counterclockwise into thinking about where things get encoded in frequency space, right? Yeah.
Thanks. I guess as like a follow-up to that, is there any reason or use for the momentum states in the directions like orthogonal to the cavity mode, like transverse? And then like, does it matter on the timescales for like whether the atoms, based on their momentum recoil, stay within or exit the cavity?
Yeah, great question. So in order to deal with the transverse part, that's why we have the repulsive donut mode, so that they don't move off axis, okay? We do, I didn't tell you, but we do the normal sort of PGC, and then we do a Lambda-Hams gray molasses, and then we finish that with degenerate Raman cyabin cooling in the transverse direction, so we're at about 0.9 microkelvin in the transverse direction. And it's just better if they're on axis. Everything gets better if they're on axis in that system. Could we use the transverse dimension? Yes. The number of phase control that you need to implement is a little bit tricky because now you have path links that you have to stabilize that are not very well defined. And it's unclear to me at this point what you gain by doing that. Like, it's definitely there. So if someone could tell me a story that there's something that we really gain from doing that, I'd be happy to do it. But it's not clear to me how much more we gain. There are systems where people drive matter wave interferometers where, depending on how you write fringes across the cloud, I think Mark was maybe the inventor of this, or someone in his group was the inventor of this, where they, in fact, they get like, is it 3D acceleration sensing by looking at sort of, you get a fringe across the cloud and the orientation of the fringe and the periodicity of the fringe tells you about like where the acceleration is aimed and what its magnitude is. So there are cases in matter wave interferometry where it's useful.
I have another quick question. So for the full photon process that you created, effectively the two-axis twisting, like theoretically, like the one benefit is that you can achieve a higher squeezing limit compared to the y-axis twisting.
Yeah.
But is that below the detection limit in your experiment right now? Or?
Yes, one of the things you give up in that process is you have to ask, how detrimental is superradiance if a photon does leak it out of the cavity to your squeeze state? And at the moment, it feels like there is a win using the two-axis counter twisting, but it's not clear if it's like a gigantic win. So I feel like we don't really know the final story on that. The three-body, were you asking about the three-body? I don't think you were. I think you were asking about the two-body.
Yeah,
yeah.
It's like three-body better.
The three-body, there is a regime in which it looks like you can generate the entanglement faster. So if you have other competing decoherence mechanisms, it seems like there could be some regimes we can identify where it would be better to use a three-body. To some degree, if I put on my hat of, I would like to build interesting quantum states. That seems like an interesting quantum state to build. So it'd be fun to do. Then if you put on your sort of, I want to do precision measurement hat, then it's a question of like, well, where's the win really come from? And I think there are some regimes where it might help you. Did I answer your question?
Yeah.
Okay.
I was wondering if you can say a little bit more, actually, with your precision measurement hat on, about kind of prospects for tests of fundamental physics, using either entangled clocks or entangled matter wave interferometry, or maybe even extending these cavity-based techniques to more massive objects, which I think.
Good.
Yeah.
So here's my take on what non-classical states do for you. I can't tell you whether or not I can help you using entangled states until you tell me the classical constraints. So here's my version of that, which is the extreme version. You may all know that in LIGO, they use squeeze light. It's pretty amazing. Actually, sort of the number of events they can detect has gone way up as a result of doing that. Fantastic. But let me ask this question. Did they really have to use squeeze light? Not really. They could have just gone back to Congress and they could have said, could you please give us another $3 billion in another 10 years, and we'll build identical LIGO detectors right next to the ones we already have. That will give us 3 dB enhanced sensitivity, and we don't have to use squeeze light at all. So the classical constraint was time and money, right? So in any kind of precision measurement task, I think you should think of it as a resource. And the question is, what are the classical constraints? And if the classical constraints are such that actually there's some other boundary condition that says it makes sense to use squeezing at this point. Just like with LIGO, they said it's going to be a hard ask to go back to Congress and ask for whatever, I'm going to make a number, $10 billion, right, in order to build another one. Now, that could be laser power, how many atoms you can effectively load into sort of a lattice. It could be interactions between atoms and the lattice. I'm going to call all of those classical constraints. So that's not a very satisfying answer, but I think that is largely the right answer.
I guess I just want to follow up to ask,
Yeah.
what if what we're looking for are surprises about the interplay of gravity with quantum mechanics?
So I do think that if, for instance, there are lots of people that are thinking about, can you, for instance, put two objects into a superposition or sort of entangle two objects where the interaction that mediates that is gravity, right? I think that would be an example where, well, we don't know. Practically, do we expect it to work? Yeah. Let's just be honest. Yeah, it's going to work. However, how do you know? Like Michelson and Morley were definitely going to detect the ether. I'm saying this because I'm teaching modern physics this semester. Michelson and Morley were definitely going to go measure the ether. And son of a, it wasn't there, right? So, it could be the same thing. But I would say that, there are serious challenges to getting to a point where that might work. I think there are fantastic people working on it, and I think it's very exciting. So.
Is there more question? If not, let's thank James again.